more time. So let's start with our first talk of today. It's for Suki Venkatesan. I think I got that right.
Number.
Close. He's gonna talk about WaTeX and I don't know that word. It's
Hegelian.
Hegelian contradictions in classical mathematics. So, thank you.
Thank you. It's so nice to be in Brazil, and it's looking so beautiful, this place. I love to be here. I love to be here for a month, right? But I've been in Indian Western Ghats, and this reminds me of that jackfruit, and so. But it's a beautiful country. I would love to stay here for long. And my talk has two. It's a little bit loaded, so I'll start with the simple one, which is we'll start with LaTeX. So you get the context, but it's a generalized philosophical approach. So I would only indicate some bits of it. Some bits are loaded, so some bits are better said, not said explicitly. So the thing about is that I'm now working in a company that's has lots of commercial products like Proof Central, Page Central, Author Cafe. But I also do open source. Now you can see already I'm in a contradiction, right? So the contradiction has started, right? So we live with those kinds of contradictions. But I'll start with WaTeX and show you a nice little contradiction there. I have to mirror it, I think, right? Maybe I mirror this. So there's this document. I created a software in GitHub called WaTeX. Initially I named it WaTeX, but there was another one already with WaTeX, so I now changed it to WaTeX or whatever. This is meant to be a kind of WYSIWYG approach, but I'll tell you the problems. As soon as you try such a system, you'll see that there's trouble. Now, what you can do in this kind of system is you can click here. I can go and change, right? And then it should change there. I forgot a backslash here. Right? That changes it. And you want to do a different equation, you click on the different equation and do the same thing. But this is the TeX approach. But if you want a WYSIWYG approach, you double click on this. So now you get to your WYSIWYG system. Right, and then now you can do the same thing here. You can put A plus B and all that, right? And then if you want, so you withdraw the mouse, it goes and puts the text. Now let's say you want to do a fraction, right? Then you do is then do A plus B, then pull the mouse, it comes to the next one, right? So you could do it this way. So now you can see that we already in a hybrid system, in the sense that I can here use both LaTeX and WYSIWYG. And WYSIWYG alone fails miserably, because let's say you want to get a character like, for example, I was searching for Aleph character, the curly N, right? I was wondering, where is this Unicode fellow? I went to the Unicode space, and it took me a while to get the Aleph. Whereas in math, I know if I type Aleph, I would get it, right? So let's say I want to type gamma, right? And the trouble with a little bit of this thing is you need something like auto-completion or something. So what you do is control backspace, then you get that gamma, right? Then you pull it out, you get the gamma. So you can keep doing this. And if you have a fraction here, like here, you can go there and then type whatever, right? So beta, right? Control B and then do the auto completion. So I have kind of two kinds of auto completion. One is control backslashes for Greeks, and if you have control slash, you could do something else. So and also another thing is you can do your own thing. The code is very little. Its code is quite simple. So it's like 20-30 lines. And if you want matrix, right, you do this. So this is like my own notation. It's a TeX notation. What you do is you type it there and then pull your mouse out. It comes like this, and then you can do whatever, 2 plus 3, 5, right? And then you want to do something like you want to put some gamma, whatever, alpha, right? Whatever. Now, this is the kind of thing you can do. So this is, as you can see, that suddenly we have a system that looks like a WYSIWYG, and if you try it as a WYSIWYG, it's going to be trouble because it's going to be very difficult. It's very difficult to work on such a system because I've tried it with WYSIWYG system like this, right? And in this slide, if I keep going in this slide, right, if you see here, I needed a subscript here, like you see here, the aleph here, right? So I was working with PowerPoint, and then I couldn't do this. Because the WYSIWYG system, you could only do superscript. The option goes there like subscript, superscript, and you don't know how to do a superscript or superscript, and then it's troublesome. So you can see that there are limitations of WYSIWYG, and if something like a TeX-like system worked within the WYSIWYG, that would be better. So you can see already hybridized systems seems to be the way. The WYSIWYG alone doesn't seem to work, and the TeX-like systems also need a little bit of help because it needs to work on something which is halfway there. So this is the kind of contradictions we face. Like I use Cortex. Cortex is a kind of TeX-like quality on the browser. So I'm trying to make a WYSIWYG kind of WYSIWYG, and it's not really WYSIWYG. It's a hybrid between TeX and that. So you could do your TeX and you could do something like a WYSIWYG. And keyboard shortcuts are also another way of Knuth used backslash because backslash is rarely used in typography, right? So that's why he used backslash. But nowadays these operating systems have control and alt and those kind of characters. So you could make them trigger there also. So the JavaScript file I've put on GitHub, it's quite small. People can easily manufacture their own thing. But my idea is that they should manufacture their own thing. They shouldn't go for very strong dichotomy this way and that way. They should find some hybrids. That's very creative. And there is also the same thing I was trying to do LaTeX, and then I found that I had to compute math. Now suddenly I see that even if you use LaTeX or content MathML, you're not able to compute them because that's at a different level. Because the form and the content, there's tension between form and content. This contradiction starts again. Like now, do I do content MathML? Then if I do content MathML, how do I present it? Because presentation then becomes difficult, right? So can we do both? That's something I'm trying. So we created something called mathml.in. There's a website where I'm trying to do that. See, it's not really things I'm doing. They're not complete. They're just ideas. But I'm trying to bring some kind of creativity there so that we can move it forward. So now I'm going to talk much more generally about contradictions. Like Pauline was telling me that day about how these people from the mountain edges come into the city, and then they work in here, and this whole city operates on this big contradiction. There'll be no Rio de Janeiro if that contradiction did not exist, right? So it's not like contradiction is something that's negative all the time. It operates at a certain way. And then if you see your left and right, right? So you see your left and right hands, right? There's this asymmetry between left and right, but this asymmetry, if it was perfectly symmetric, there will be no such thing called left. So which means that symmetry is broken. In fact, they found in physics also the equations, the left-right asymmetry is broken. There's a famous scientist, Abdus Salam, who first proposed that left-right symmetry is broken in physics, right? Who got a Nobel Prize for that, and the grand unification started after that. So the left-right symmetry breaking is a very nice thing. For example, if you look at, the idealism is more about symmetries, right? And reality is about breaking it. So for example, you take Earth. The Earth is a perfect sphere, right? So how is it that we have mountains? If it's a perfect sphere, we shouldn't be having mountains, right? But we have mountains and rivers, which shows that it's not a perfect sphere, right? But people tell us that it's a sphere, but I would like to know whether it's a sphere or not, right? If you look at it in the 1-0 dichotomy sense, then it's not a sphere, right? But if you look at the radius of the Earth, it's something like 4,000 miles, right? And if you see what's the deviation of the radius, the worst deviation you get in the equators, which is it's a little bit flat there, so it's like 14, something like 14 miles less or whatever, right? So which means 14 by 4,000, so it's 7 by 2,000, so it's like 0.35% deviation from, so it's 99.7% a sphere, right? So suddenly you see that to answer these qualitative questions, you have to go into quantity, right? Now again, see the quantity contradictions come. Now the other interesting thing is we are in front of it. That is, if you see nuclear forces, like for example, you take a uranium atom, right? And then uranium atom, there's a little bit of tension there because there is this there's this Goliath who is holding the protons together, right? He's holding it together, and like Goliath is, he's strong, he's big, but he can't run. See, he can't fight at far distances. And so, for example, David comes to attack him. Goliath will say, "Come near me, I'll fight with you." Because he can't come, he can't fight him if he's far away, right? And that's the advantage David has. David has a catapult, and then he hits him hard on the head of Goliath. Goliath falls because those stones are really like bullets, David that can answer. So he hits him hard, and then he falls down. He takes his own knife and cuts him off, right? So Goliath is only strong when he's near, right? It's like a sumo wrestler asking you to come to fight, And if you take a stone or a gun, right, it's no match, right? The sumo wrestler is no match. So the same way, the electric forces only operate at distance, right? And the nuclear forces operated. So when the uranium atom gets bigger and bigger, right? You can't have any atom bigger than uranium because it will break down. Because the protons are now too far away, so they will repel each other and break apart. Exactly the reverse situation happens in the sun when there is hydrogen atom, right? And this hydrogen atom is ionized, so you only have the hydrogen protons there. So it's basically protons, and protons have this thing that if they are brought together at a very small distance, the gravitation of the sun is pulling it together, right? And so they're too near each other. So now the Goliath is taken over. So what's happened is that it comes near, there's a lot of energy release. So you see that every contradiction releases a lot of energy. Like when Paulini was telling me about all these people coming in and how a little bit of money you put in them, it kind of blows up. So you'll be surprised, like there's so much energy released there, right, in those contradictions. But the main reason I came here was another reason. There's a guy called Newton da Costa from Brazil. He's from Sao Paulo, and there's a guy called Quezda Contreras. These guys have come up with a new logic, which has solved a very difficult problem, which is that, see, one of the problems which has been bogging all philosophers and logicians for a long time, for many centuries, has been that if both a and a minus a is true, then we have all sort of the whole classical Boolean thing blows up. So, for example, if you have this, if both if you see this a or b, so you take this Boolean thing, right? A or b and minus a or b, and if it is true, right, then you can see that you can prove that this implies b is true, because for both to be true, right, b has to be true. For both this to be true and this to be true, b has to be true. Because in classical logic, we know that if a is true, then minus a is false, right? So one of the big problems is that in classical logic is if both a and minus a is true, then you can show that b is true can be shown, right? So which is a blow up. So what these guys have done is basically contain this blow up and come up with there is a name coined by this guy called para-consistency logic, and that's the logic that is required for physics to evolve to next stage, that is quantum. So if you want to go for a logic that explains quantum logic, and it's not something far away, because quantum computers are looking like going to happen, right? And there's a reason why it's going to happen. But I'm not going to talk about this. This is a very complicated thing. Even I have no idea what that is. But I just want to mention that there are two interesting guys working on it. And the other reason why I wanted to come here was another interesting reason. These guys, I didn't know that they came to Calcutta. So they say that they've been in the institute where I did my PhD. It's a very the hustle bustle of Calcutta is, and it's very polluted and all that, right? But there is a cozy little oasis within Calcutta called Indian Statistical Institute where I did my PhD, right? Where you can sit beside the ponds and do your PhD. So these guys came there and they loved the place, and so they mentioned that, so this was something they came for a conference there, and they seems to have other people there who seems to agree with their logic. I'll go to the next slide. Now let me go to a little bit of, from now on I'll be switching to a little bit of serious maths. But it's not a maths that's not accessible to other people. It's not like too abstract. So we have the classical Zeno's paradox, right? So I'll go into, the reason why I want to deal with this is that, when you see contradictions, right? There are contradictions at one level, and there are contradictions at a higher level, and it builds up, right? And sometimes people at one level deal it at that, instead of dealing at that level, they deal it at this level. For example, we have Intel, who is a monopoly, right? But it's a hardware monopoly. And then on top of that, you have Microsoft, that's a software monopoly, right? And on top of that, you have Google, and top of that. So when you're dealing with contradictions, you deal it at that level, right? So sometimes people make solutions that this is the big enemy, or that's this thing, and then there is this contradiction. But you have to know that at each level, each is different, right? And you have to deal with them in that way. So in Hegelian, Hegel is a German philosopher. Like, he found that these contradictions can be resolved at one level by the next level and next level. So you get a kind of abstract pyramid, like the one you were saying, data, and there was next layer and next layer. So Hegel solved this. So I'll describe the Hegelian logic in terms of classical maths, right? And so you take the Zeno's paradox, right? And you see that, like if you take a glass of water, right? And if you start counting the number of drops in a glass of water, it's infinite, right? So the same way, if you start counting the number of points in a straight line between 0 and 1, the number of points are infinite, right? But at the same time it's a finite length. So, for example, I remember many years back in India, they used to sell bananas by their numbers, right, dozen bananas this, right. But sometimes you have these big bananas and you have the small bananas, so it becomes a kind of problem, for them. So then they started doing it by kilograms, right. So now suddenly they, instead of counting, they went to a system of continuous system, like 1.5, half fractions and all. So and also because nowadays they have those calculators, right, with them, so they could do that. But in those days they couldn't do the calculation, so they went by numbers. Right? And you see that in numbers you have all kinds of numbers, right. So you have integers and then you have rationals, right, and these are countable in the sense that you can count them 1, 2, 3, 4, 5, 6, right. And there are these numbers, so called numbers, which are uncountable, the numbers between 0, 1, right, or something like milk, or if you want to count the number of drops in a milk, it's impossible, you can't order them this way. And then I'll be talking about something which is in between, between the uncountable numbers and then the countable ones and the continuum. I'm going to show you that's something in between. And then we have this so-called transcendent numbers. I will talk about it. That's more to do with complexity. So first I'm going to prove it to you that real numbers are uncountable. This is a very simple proof. So what you do is you write the decimal number between 0 and 1 in terms of a binary decimal, right? And then assume it's countable like this, A1, A2, A3, and then you have a system that counts it. This is called Cantor Diagnostician. So what you do is, if the first one is 0, then you put 1. In the second one, if it is 1, then you put 0. In the third one, you look at the first decimal of the first one, second decimal of the second one, and the third decimal of the third one. I made it gray. Can you see the gray? It's gone. It's sad. I should have made it darker. So I made them gray. The first one, so you do this one, and this one. It's more like diagonal, they say. So you get this kind of number. Then you can show that this one is not an element of this. Right? That shows that it's a contradiction, because you said that you could count everything and you can't. It proves that you couldn't. So this shows that real numbers are not countable, uncountable. And you can also show that there is a bijective mapping between subsets of numbers and the real number between 0 and 1. That is, so you take any binary number like that, right, and then create this subset. That is, if the second one is 1, so find where are the ones, right. So the second one is 1, so you put 2. The fourth one is 1, so you put 4. So you see that given a binary number, you get a subset of x, subset of integer, right. And you could do the same way, like you given a subset, you could from that put ones there where the subset is, right. So then you can see that there is a one-to-one bijective mapping from real numbers to subsets of integers, right. So that shows, and that's called a power set, and but symbolically they write it as 2 to the power. So if natural numbers is Aleph, then the continuum is, so this is only a symbolic equation, so it's not really maths, but it's a kind of symbolic maths. So what they mean is the power set of natural numbers is C, right. So the interesting question is there something in between, or there infinities in between, right. I'm going to show you there is. So in classical contradictions, so Hegel showed that there is a hierarchy of infinities. I forgot to mention that basically if you do this power operation, you can keep on doing the power operation. So you can create set of all subsets and then create a set out of it, and then take set of all subsets of that set, right. You can keep doing the power set. So that way you get a hierarchy of infinities, right. And if you come to India, I can show you a hierarchy of infinities. You have small demigods. You can have then those demigods report to other gods, and you can have layers of gods. You think of gods as infinities. So you can see that there's layers of gods who report to each other, you know. Now I'm going to show you something very interesting. This is the core of the lecture actually. That I'm going to show you that there is an infinity. Again, all this was created by Cantor way back, like 100 years back. So I'm going to show you a very interesting stuff. So what you do is you take a interval 0, 1 and take the middle 1/3, but don't remove the endpoints, but just remove the middle 1/3. So you take the interval between 0 and 1/3, including the 1/3 fellow, and then from 2/3 to 1, including the 2/3 fellow. So you get 2 ones, 2 bits, and you keep on doing this recursively, right? Then very strange thing about that is, so I can't do this in computer, maybe you can do that, I'm not good at it. So you have this big line, so you have the middle 1/3, so this is taken out. So this is taken out. Then again I take the middle 1/3, this is taken out. This is taken out, and you keep on doing this, right? And then you will get, this is not empty because those endpoints are there, right? This is not an empty set, and those endpoints are there, and so because of that it's a non-empty set. And you see that this set is of dimension log 2 by log 3. That is, it has dimension in between 0 and 1. So there was this fellow countable points which had 0 dimension, and there was this fellow 0, 1 which is basically a line, so it has 1 dimension. So I'm going to show you something which is fractional dimension between them, which has dimension log 2 by 3. So the thing is that how do you define dimension, no? So if any object, if you scale it by 2, then if you get 2 to the power n copies, right, then it's dimension n. This is called scaling dimension. So you take a line, if you double it, so if 0, 1 is doubled, then you get 2 lines, 0, 1 and 1, 2, right? So 2 pieces of that line you can put next to each other. So if you double it, you get, and if you take a square, right, and if this was a square, if you double it, you get 4 pieces. So this is 2 to the power 1, this is 2 to the power 2, and if you do it a cube, you'll get 2 to the power 3, right? So if you scale something by a and it grows by a to the power n, right, then it's of n dimension. So that way, for the Cantor set, if you multiply it by 3, you will see that you will get 2, right, which means n is log 2 by log 3. Right, and there's an easy way to get a feel of the Cantor set, which is this, you know, that you take a trinary representation, that is, instead of binaries you take 0, 1 and 2, right, modulo 3, right. So you operate in modulo 3, then you can write all numbers with 0, 1 and 2, right, and those numbers that only have 0 and 2 in them, they are the Cantor points in 0, 1, right, because the one in the middle fellow will not be there because that's the one that has 2 in it, right, that's the one that has 1 in it, sorry. So this one has 2, this one has 0, this one has 1. So the one with missing ones, that's the Cantor set. And you can, this is uncountable already because we showed that for the one case, if it's a number with 0 and 1, we already showed it's uncountable. So with 0 and 2 also it should be similarly uncountable, right. So it's uncountable set, but it is it has a scaling dimension is fraction. Oh. That's it. Now the thing is that all nature has decision problems, right, nature. So there's a thing about computer science here, like, so all algorithms are reducible to a natural number. So all algorithms because of, see, when you run a program, finally you get a exe binary file, right, to run to the machine. So that binary file is a byte, right? So it's finally an integer. So all algorithms can be enumerated. So they're enumeratable, so they're countable, so they're equal to this thing. So they equal to a natural number, so they're countable. Decision problems, on the other hand, they are uncountable. They're like mapping from natural number to 0, 1. So that's the binary real number, right? So decision problems are uncountable, and programs are countable. So there is this thing that people say, because one is uncountable and this is countable, there'll be lots of problems that you can't solve. But it's not really true, because if you see, for example, fractions are uncountable, but they can approach any number to any approximation, right? So that way, although exactly solvable problems may be limited, there may be many problems that are not exactly solvable, but as an approximation, you can approach any problem to any degree, right? And that's the power of things like machine learning. So that's the contradiction, because at one level we say it's countable and this is uncountable, but you can see the rational numbers are dense in real numbers. Then we have algebraic irrationals also, like root 2 and all that. Even they are countable, right? So the thing that is uncountable is the transcendental numbers, right? The core of uncountability comes from them, right? Because even the square root of 2 and all that is countable, because if you take polynomials with rational coefficients, you can count them. Now, so because of this NP equal to P, the answer is no. But this answer depends on, like I said, no, if you count bananas the traditional way, then you won't get this answer. But if you count it using scaling dimensions in a better way with a sensitive measure, then you can show that NP equal to P is not true. And this is true of even physics. You have this so-called second order phase transition. So you have what's it called in physics, you have first order phase transitions, like when you heat water, at a certain moment it becomes gas, right? But so we only know of states like solid, liquid, gas, plasma, 4 states of matter. But you'll see that strangely there are states like glass. Glass is neither here nor there, right? You have liquid crystals and those kind of strange creatures. So they're there because sometimes you get that second order phase transitions, right? Those are so reality is like that. They're like in between states. So one of the big puzzles about neural network is that why does it work, right? Why does it work so well, right? And people are surprised because it doesn't have the power of all of maths. It's got only limited maths in it. But why does it work in reality? Because of this reason that nature has lots of these constraints and controls. So the iterative approach, we saw the Cantor set kind of iterative approach actually works, right? And transcendental numbers are above that, because they're beyond that iterative approach. So they could be related to NPR. So these are just ideas I'm developing, so they're not concrete yet. And you can see that it's not always true that if the decision problem is NP or P, solvability is trivial. We know like Fermat's last theorem is so simple to state, in one line, but it took 700 pages to prove and so many scientists to verify, and that's it.
Questions, anyone? All right, so thanks very much, Suki.